PLC selection, components, and communication. Objectives, we're going to identify important questions to determine which PLC device to purchase, which technicians will not be you guys' problem. Select modular Allen Bradley Slick 500 series components. Select input output modules for Allen Bradley Slick 500 PLCs. Nope. We're using Micrologic's 1400 in here, so recognize how to connect sensors and switches, describe different types of PLC memory, explain how Micrologic's PLCs communicate with other industrial devices and components, describe the method of connecting PLC devices to programming modules. The only programming module we will use is our PC. Can also get what is known as a DTAM module, which is a data terminal something. I can't remember anymore. It's been too many years ago. Basically, handheld programmer that is essentially obsolete now. Compare the features of Logix 5000, Logix 500. List features of the controllers in the Control Logix family. Yeah, we're really not going to worry about Logix 5000 or Control Logix. Summarize the industrial control design process. Explain the design setup of HMI and industrial control systems. We're not going to really get into HMIs in this class either. Actually, HMI is a very generic term. Does anybody know what HMI stands for?
Yeah.
Good guess. Absolutely not right.
Something interface.
2/3 right. The M is machine. Human machine interface. That can be anything from push button and pilot light all the way to full blown SCADA computer system. For our purposes, we're going to use the term OIT. Anybody have a venture as to what an OIT is?
Something, information, something.
No. An operator interface terminal. When you hear the word terminal, it means electronic device, which is basically the touch screens that we have on the black trainers that you will not get to play with in this class. We do touch them briefly in PLC2, but you don't really get to start playing with them until you get into advanced automation, otherwise known as PLC3. PLC selection factors: manufacturer support, cost and serviceability, flexibility, expandability, programming software, training, and documentation. Manufacturer support is probably one of the most important ones, especially whenever you're first starting out in your career. Rockwell Automation has what is known as I'm drawing a blank here. Tech Connect. That's it. I know I'd think of it eventually. It is paid service. There are two levels of that. Either 9 to 5 only or 24/7. Unfortunately, their 24/7 doesn't cover everything. The guys and gals that work in their drives group are 9 to 5, Monday through Friday, period. you have a drive problem at 5:01 on Friday, you are not fixing it till 8 AM Monday morning. Unless you just happen to get lucky. Or you Google it. I've fixed many of them by Googling it. Cost and serviceability. Generally speaking, your customer is going to tell you what controller platforms they already use. And they will say, please get me one just like it. So it has less to do with cost than it does customer specification. Flexibility. All the MicroLogix controllers that are in use today are both expandable and flexible. Programming software. Say what you will about Rockwell Automation, but they have by far the best programming software. It's the most user-friendly and prettiest. Training, that's what we're going here. Documentation, Rockwell also has one of the best documentations that you can get. And this is an excerpt of the programming manual for the MicroLogix 520 series drives, which are the ones on these trainers. So, let's start over here. Flip through that fast enough. Allen Bradley controller components. There again, this is for like 500 as opposed to MicroLogix, but many of the modules that you see listed on here in the 1747 or SLIC family is
You're wanting to read through everything.
no, I said flip through it. You know what? I've got a few of those up here, so let's just do this. Anyway, the 1747 family is the SLIC. The basically the same control or the same modules are available for the MicroLogix family. It's just the 1762. It's the first four digits instead of the 1747. Modular Allen Bradley PLCs have a chassis, power supply, processor, and I/O modules. Those are the four basic components of any PLC. However, the MicroLogix family, it is the chassis, the power supply, and processor, and the base I/O is all in the same physical piece of hardware. They are expandable though, so you can get expansion modules. And trainer number 1 and trainer number 2, these two right here, have got an extra 16-point input module on. Chassis and an AB small logic controller or SLC 500 SLIC provides electrical current to processor input modules and output modules. Same thing on the MicroLogix. 4 chassis sizes for modular SLIC 500, 4, 7, 10, and 13. Really don't care about that because we're not using SLIC. Number of slots can be expanded to a maximum of 30 by interconnecting up to 3 chassis using cables. That's for SLIC. On the MicroLogix, you can have a maximum of 7 expansion cards. Try to put the 8th one on there, it doesn't work. When installing PLC components in a chassis, the processor must be placed in slot 0. I/O can be in any other slot. Slot 0 is moved reserved for the PLC or for the processor. The same is true with the micrologics. The onboard I/O is all slot 0. We'll talk more in a little bit about the way you address those. Complete unit includes all the pieces. I/O module is referred to as module 0. That is the processor itself. I/O port types and voltage or current rating cannot be altered. So if you get a 24-volt module, you can only use it for 24 volts. If you get a 120-volt AC module, you can only use it with 120 volts AC. That sort of thing. You can buy relay modules, which allow you to mix and match to a certain degree. There is a common terminal, 2 common terminals on the relay output. You can set them up, one of them is 24, the other one is 110, or 110 and 24, whichever way. Or both of them, 24, both of them, 110, whatever you want to do. 2 slot chassis can be added, so 2 more I/O modules. That is not, that's slick stuff. Really need to get in here and update these PowerPoint slides. Power supply provides power to the chassis backplane and thus to the processor, modules, and peripherals attached to the chassis. That is also true with the micrologics. The backplane on these actually comes up front. This ribbon connection here. But the power to operate the logic on the module is comes through the backplane. The power to turn the inputs on is an external supply. Power supply must be able to provide ample current to these components. Say you have a maximum of 7 expansions on micrologics 1400. If you try and put an 8th one on there, like I said, it doesn't work. Not only can you not address it, but the power supply doesn't have enough current available to drive the 8th module. Add the current ratings of processor, I/O modules, communication modules, special modules, blah, 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 blah. And then make sure you got a power supply big enough. That's much more important on the SLIC than it is micrologics. Those are the micrologics, or the SLIC processors, 501 through 505, based on how much memory is available on them more than anything else, and the communications. The 501, I want to say that was a DH485 processor for communications. 502 was DH485, 503 was DH485, 504 was DH plus, and 505 was Ethernet. Allen Bradley series modules, digital or discrete I/O. You guys remember what discrete is? on or off. Analog. Between a minimum and a maximum value. It can be anywhere in between. Actually, that's not true because there are discrete steps, but there's enough of them to pretty much say that it's infinite. Especially modules and distributed or networking modules. You do have those with micrologics as well. They're just not in the rack. Each input or output module has several ports or terminals. For example, input module 1 may have 16 ports and output module 2 may have 8 ports. That's accurate for micrologics as well. Ports on modules are specified when they are specifically used in ladder logic diagram and are addressed by their module and port number. A typical micrologics or Logix 500 address have I for input. Makes sense, doesn't it? Oh, by the syntax is everything. The syntax isn't right, doesn't know what to do with it. Colon. And then we're going to start at slot 0 with the controller itself. Then slash, and then the port number that we're going to use. So start in the basement and put 0/0. Then you go to 0/1/2/3 and so on. We're going to learn a lot more about addressing as the semester goes on. The first character tells you what data file you're dealing with, whether it be input, output, system file, timer, counter, register, integer file, or floating point variable. The colon says, okay, now we're done with file. Go to slot number. Always start with 0. And then up to 7 from there. The slash tells you that you're talking about a bit level address or a single discrete point. And then they start at 0 and go up to however many you have on that in particular module. The base unit on these micrologic 1400s, there are 20 discrete inputs. So it starts at 0, goes all the way up to 19. And then on the outputs, it would be O:0. You only have from 0 through 11 on the outputs on these. Different connections that you can make to the modules. Thermostat, motor, normally open switch, normally open green push button, normally open red push button, blah, blah, blah. You guys can read. That is an example wiring diagram. Pretend that plus 120 volts is actually plus 24 volt DC. Then your outputs, that would be, if it's a relay output, can be 24 or 120. Wiring. I/O ports typically rated for low amperage. Ordinarily connected to I/O devices through American Wire Gauge or AWG size 14. An AWG 14 gauge wire is capable of carrying way more current than the module is capable of carrying. So don't use the wire as fuse. Anything you're trying to switch that has a higher than a few milliamp current draw, you want to put a relay in between them. That is what is commonly referred to as an interposing relay. Remember that term, you will see it again. Most applications output devices require larger voltage and current ratings, hence the need for the relay. And that relay should be used to connect larger equipment to output devices. PLC output port provides voltage and current to the input coil of a magnetic relay. You guys familiar with how relays work? What I mean? One of the things that you learn in electricity 1. Shows their output 4 is connected to coil and relay, and then the relay itself is operating motor number 2. Sourcing and syncing. This confuses a lot of people. Sourcing device always attaches to a syncing I/O. A syncing device always attaches to a sourcing I/O. Okay, it's all about the way that the current flows through the input or output module in a DC circuit. They are labeled syncing and sourcing. I always got to think about it. Have some supply, switch, input module, and there is a terminal on module that gets connected to your 0 volt. The current is going to go from the plus 24 volts through the switch to ground, so it is syncing. And then yeah. This way the current goes Okay, so it's sourcing. We won't get too deep into that. Sourcing occurs when current flows out of the port. It occurs when it flows into the port. Yeah, that's a sinking input. User memory holds a ladder program. About 75% of the total memory. System memory stores the information needed to execute the user program. And then you have the input and output status. Here's the rest of it. Timers, counters, math functions, logic functions. That's a special part of the memory where the ALU and the logic functions store their temporary data. That's just a layout of how the memory is segregated in the controller. They just mirrors this slideshow like extremely boring.
Funny since you said.
I haven't put anybody to sleep yet, though, haven't I? A little bit. I promise it gets better. PLC communication system. PLCs communicate with industrial input-output devices and peripheral control components. Peripheral control components include PCs, printers, display panels, peripheral interfaces, and programming devices. SLC 500 PLC, channel 0 is used to attach peripheral devices. Channel 1 is used to communicate with other PLCs and PCs. That is also true on Micrologics. Channel 0 on the Micrologics is RS-232. And channel 1 is Ethernet. Network communication is DH45, DH+, Ethernet. You can program the 0 port on Micrologics 1400 to do data highway or DF1. Most common of which is DF1. They'll also do ASCII and a couple others. Anybody know what ASCII is? Huh? Yes, Warren, what do you got?
Isn't it like just art using key, different like characters?
Yeah. American Standard Character for Information Exchange or something like that. It's basically predefined. This bit pattern equals A, this bit pattern equals B, this one equals C, and so on. Two types of DF1, full and half duplex. Full duplex just means that both devices, one on each end of the link, are capable of listening and talking at the same time. And half duplex means that you can only listen or talk. You can't do both at the same time. If you think of telephone, we can both listen and talk at the same time. That's full duplex communication. CB radio, you can only listen or talk because you got to press the button on the mic to be able to talk. And if you press the button, you can't hear. ASCII allows for communication with other devices that use ASCII protocol, serial printers, barcode readers, that sort of thing. Serial communication data is transmitted 1 bit at a time through one transmission medium. Can be framed prior to transmission. Serial communication generally says, hey, this is the start of a frame. Here's the data. Okay, now we're going to stop the frame. Baud rate. You guys know what the word baud means?
Right?
No.
It's like a bid.
Baud is actually an acronym. Bits of actual usable data.
What was the last one?
Data.
Yeah.
Bits of actual usable data, which means you can shove a whole bunch of ones and zeros down the line, but if you send them too fast, you know, you can talk faster than I can listen. I'm not going to get everything you say. PLC may operate at a rate of 19.2 baud and CPU, with the CPU, and 2400 baud for the printer. 2400 baud is really slow. 19.2 is by today's standards. You can actually get up into 300,000 plus range with today's technology. Anybody in this class ever used dial-up internet?
Yeah.
Yeah, my first computer modem was 300 baud.
The normal gateway or something.
You could, no, it was an Atari. But you could watch it, type characters on screen one at a time, 300 baud. Really, really slow. I thought that I was shitting in tall cotton when I got my first 2400 baud modem. And then my brother-in-law got a 96K, it really pissed me off. Framing, process of indicating beginning and ending of transmission. Framing bits include start, stop, and parity. Parity is just a real quick down and dirty way of simple error checking. You know, if you, yeah.
It's actually going back and reevaluating, like recalculating,
Well, the way parity works in serial communication is it count, you know, you have X number of digits, say 8. If you add those 8 digits together, do you get an even number or an odd number? So if you have 1001110 1, okay, that's 1, 2, 3, 4, 5. There are 5 ones in there, so that would be an odd number of ones. So your parity bit would be a 1. Okay. But with a 0, you can only have 4 ones, so your parity bit would be a 0.
that go again with the baud, as in like the actual useful information. It's useful.
Yeah, that's part of the parity bit is part of the baud rate. We're not going to deal with serial. We live in the 21st century. We're going to use Ethernet on everything.
It would be good to know that before we got to stuff that we're actually reviewing.
Do what?
So if you get to know that, it's kind of like playing on an Atari and playing on a modern day game. It's good to see where it came from.
Agreed. We can break out the DF1 adapters and play with them.
This isn't related to chapter 2, but for some reason, I thought that we would be doing the chapter 1 quiz at the start of this class, and then
No, chapter 1 quiz was due at the start of this class.
Yeah, I did not know that.
Parity bit check is used to find transmission errors. Errors come in the form of lost or changed bits. So depends on how many high bits you've got in your transmitted data. If you have an even parity, then even number of bits will give you a high on your parity bit, and an odd number or odd parity will give you high on an odd number of parity on your parity bit. Also, the option to have no parity. DTE and DCE. This is on the quiz. DTE is data terminal equipment. That's the guy that's doing the talking. And DCE or data communication equipment is the guy that's doing the listening. Channeling systems. This is on the quiz also. Simplex, you have one talker and one listener, period. App duplex, you have one talker and one receiver
But not at this.
in one direction or the other, but you can't talk in both directions at the same time. CB radio. Simplex, if you think of your television, you can never transmit from your television. And in full duplex, everybody can talk and listen at the same time, just like on your telephone. That just explains what I just did. Programming module, handheld dedicated personal computer. We're going to use personal computer. That's what an old slick T10 looks like. Force mode caution. Forces in your PLC is you are forcing an input or an output into a known state. Yep. You have to be really, really, really careful and know exactly what you're doing if you're going to force inputs and outputs. It's really for troubleshooting purposes only. Because you can do really bad things to the equipment, or worse yet, really bad things to people.
Servicing a motor and you just kick it on.
Yeah. Has potential to cause bodily harm to assembly line workers. Personal computer or laptop can use programmed PLC. The PIC or PIC module was used with good old fashioned 9-pin D-sub RS-232 COM ports. And the UIC was used once USB became a thing. Nowadays, we choose Ethernet. Communication settings to prevent, we're getting close to the end of this cockeyed thing. Used to prevent unauthorized personnel from running or altering the PLC program. Most PLCs have different hardware and software. COM settings off. System cannot be run or programmed. Offline program, the PLC's program can be modified while the system is not running. Disable turns all outputs off or sets them to an inoperable state. And run, system can run, but its program cannot be altered. That's old school. Offline and run are the only two that are available on modern controllers on that list. Online monitor or run, and then remote run / those are available yet today. And then forced allow the system to run, allow the program to modify while the system is running. That's not what forced means anymore. You're intentionally driving an input or an output to a known state when you force. Remote program is what we use now for modifying the program while the system is in operation. You want to be really, really careful whenever you're doing online edits, because if you tell it to take a long walk off of a short pier, it's going. You can do bad things to people and machinery. We're not using Logix Pro in this class. Allen Bradley 32-bit control Logix 5000 family. That PowerFlex AC drive is not part of the control Logix family. It's a drive. But the control Logix is the type of controller that are in those. Compact Logix is the type of controller that's in the PLC 2 trainers. And Soft Logix is basically a industrial computer with a touchscreen built in. Network communications. All of those are true for MicroLogix as well. For device net or control net, you have to have a special interface module. Operating or scan cycle for Allen Bradley PLC. This is important. Whenever the controller is processing your user program, very first thing it does is go look at the status of all the inputs. If the input has voltage applied, then it reads that as a 1 or high state. If it does not have voltage applied, it reads it as a 0 or a low state. It will write that data accordingly into the input data table. Then it executes the program, your user program. It processes the logic from top to bottom, left to right. It cannot and will not ever go backwards. You guys ever see actual relay ladder diagram? Electricity is extremely lazy. If it can take a hard left, it's going to. In PLC logic or ladder logic diagram, power does not flow from right to left under any circumstances. That is not necessarily the case or true. If your run of logic is too wide to physically fit on the screen, it will wrap around and pick up where it left off. But logically is treating it as one big long run. It will never go right or left. And then once it processes the logic, it goes and updates the information in the output data table. If the logic says that output needs to be off, it shuts, writes a 0. If it says the output needs to be on, it writes a 1. And then, of course, whether you have a 0 or a 1 in the data table will determine whether that output is off or on. The one thing that's not included on that is service communications, which it'll go out and say, hey, Ethernet, what do you got for me? Or hey, DF1, what do you got for me? This is what I have for you, so on and so forth. And then when it gets done with all that, it starts off back up the top, does it all over again. Processors are fast enough nowadays that it does all that in just a couple of milliseconds or thousandths of a second. It's pretty quick. Motion control, we're not going to talk about too much. You can't do motion control through motion control with a micrologics. So we're not worried about it. Comparison of RS Logix 500 and RS Logix 500. I just realized that that is a typo on that title.
I bet I know the answer though.
Probably.
Entirely different.
500 is 16-bit program. 5000 is 32-bit. Logix 500 is data file based. You have an input data file, an output data file, processor status data file, bit file, timer file, counter file, and so on. Logix 5000, it uses tags to identify the I/O modules. And both of them share common Windows features and a graphical user interface, or GUI. I said earlier, Rockwell's got the prettiest operator interface. Industrial control design project organizational chart. You can say that if you want to, it's really irrelevant to this class. Electrical engineering tasks. That's the process you go through. Not trying to teach you guys to be engineers, so don't worry about that. Cost estimation chart. That's how much it costs to build one, or at least back then. Can't touch one for anywhere near that these days. Mechanical engineering. You guys are definitely not mechanical engineers.
I'm going.
I'm sorry.
Not yet, yeah, not yet.
That's not the intention of this class, to teach you how to do that, so. You're definitely not going to be purchasing or accounting as a technician. Well, you might purchase, but you worry about, somebody else got to worry about how to pay for it. Engineering and management tasks, you're not in, don't worry about any of that. Worry about any of that. HMI. Again, those that are shown on that screen right there are OITs. They're electronic devices. Human machine interface is, I'm interfacing with my computer using this little handheld doodad. Have a keyboard, have a mouse. Those are all monitor. That's all HMI stuff. The push buttons and pilot lights on these trainers, that's all HMI stuff. OIT is the electronic touch screen like these. Typical interaction among screens on a multiple screen HMI. You have the first screen and then you can select the other screens from there. It's again, an OIT, not an HMI.